Batch normalization is used to stabilize and accelerate the neural network training. So we'll understand how batch normalization does that. But before starting, we want to understand what does this normalization or standardization means. So these are the ways to scale data. So if you see this tabular data we have age, salary, height, weight. This raw data, this has different units, kgs, centimeter, rupees and all different units it can have. Here we have centimeter, rupees and all, right? So we have different ranges as well. Age is in this range, salary will have a very high range. This is range of height, range of weight. So different ranges of data we are getting. So some features might dominate. So in this case, salary is very high range, so it will dominate the other features. So this actually makes a different range of input. This makes the training unstable. So that's why we use scaling to make the learning very more stable. So there are different ways to scale the data. Normalization is called the min max scaling. So let's say we have the data in 0 to 100 range. We squeeze the data in between 0 and 1 in a fixed box. So whatever the data range, we will just squeeze the data in 0 and 1. So smallest will be 0, largest will be 1. So everything else will lie in between. So how we'll calculate that? X minus x mean, this is the mean among the data, and divided by x max minus x mean. X max is the max, x mean is the mean. So this is how we normalize any data. That's why it preserves the relative distance between the data points. The other approach is standardization. So here we calculate the mean and standard deviation from the data, and then we center the data. We make the mean 0 and standard deviation 1. So let's say in this data, this the data distribution we have, the mean was at 50 and standard deviation was 20. So after standardization, if we standardize using this formula, x minus mu, this is the mean and this is the standard deviation, we'll get different distributions where mean will be 0 and standard deviation will be 1. So the standard deviation, this tells where your typical data lies, right? It doesn't actually tell where all the data lies, just the typical data where it lies. Also, standardization is mostly used in machine learning or deep learning because it keeps the gradients balanced. So now we already scale the inputs because we saw the input data for our previous examples, right? We had age, salary, height, weight and all. So different ranges of data we had. So we have to scale the data so that our model becomes more stable. So deep learning prefers data centered around 0 with controlled state. Mostly in deep learning, standardization is used, and here in batch normalization also we will be using standardization. These two terms are used interchangeably. So if we have a tabular or numerical data, mostly standardization we use because features can have very different distributions. For image data, so image pixels will be from 0 to 255, right? So we normalize this, we squeeze it into 0 to 1. Then often we can standardize using dataset mean and standard deviation also. So our NLP also, for different use cases, based on the requirement, we can either use standardization or normalization. Now, why input normalization helps? So we saw that the input might have different ranges and one feature can dominate the other features. So if we normalize the input, it will prevent one feature from dominating. It will keep the gradients balanced. It will speed up the optimizations, and so the training will become smoother. So this is about input normalization. So after input normalization, like you see, this is before standardization or normalization, right? So the data will move here. The mean will become 0 and standard deviation will be 1. So here I am showing the contour plot of unstandardized and standardized data. So for in unstandardized case, you see we get an elongated curve like this. So one feature dominates the loss because features with larger scale make the loss much more sensitive in their direction. So it creates a steep curvature in one direction, flat in another. But for standardized case, this we get a circular curve like this, follows curve. So you see we'll get a, for gradient updates we get a zigzag path for unstandardized case. So if learning rate is high, there might be chances of overshooting. So we cannot use larger learning rates, and that's why we have to use smaller learning rate, and smaller learning rate means training will be slow. If we have a standardized data, of course the path will be smaller, path will be smoother, and we can take larger learning rates, and the training also will be faster. So now one note here is we can use AdaGrad or RMS prop also here. So because we know this in AdaGrad or RMS prop, we can have different learning rate for different features. So that is also another way of solving problems. But here in this video, we are discussing batch normalization. We'll see how batch normalization handles these problems and how it makes our training faster. Now, the key question we have is, we are already normalizing or standardizing the input, right? But why can't we normalize the hidden layer inputs as well, right? We can normalize other layers also, or at least few layers, other hidden layers also. The hidden problem we have is each layer's output becomes next layer's input. This layer's output is this layer's input. If we have one more hidden layers, then this layer's output will be that layer's input. But distributions keep changing. This is one main point where why batch normalization we need. Because every time we are doing gradient descent and we are doing back propagation, right? So we'll calculate the loss and we'll update the weights after back propagation, right? So every time this weights are getting updated, so this previous layer's output also is changing. So the next layer's input is also changing. So every time back propagation happens and weights are updated, for every hidden layers, input distribution is also changing. So all the hidden layers has to adapt to new input distribution every time, and that's the main problem. So to understand that, we'll understand covariate shift. So this is a very simple concept. So let's say when the input data distribution changes between training and testing. So we have training time and testing time data. We have this class 1 and class 2, class 1 and class 2. So in the training time we got this data, the data is here, data distribution is different. We got this model decision boundary. It's able to distinguish class 1 and class 2. At test time we got a different distribution. Data was here, now data is here in the test time. But still the model decision boundary is able to distinguish the classes. So we are not able to tell that this data distribution has changed, but the model is performing fine at test time. The relationship between inputs and levels, this probability of y given x, this is remaining same. So this model is performing good at test time. But what happens when we'll test with some other real world data? This model accuracy will drop in real world scenarios, such as when model trained on native speakers fail on non-native accents. So if we try on any other different real world scenarios, this model will not perform well. It performed well in test time because it got lucky, right? But it will not perform well in other real world scenarios. So this is the problem. This problem we call it covariate shift, because the covariance of the data, this is shifting. Now let's say one more example here. We have car and non-car data. So let's say this is training time and this is test time, right? So at training time we got this car data and non-car data. It found some decision boundary. At test time we got colored car, right, and non-car, right? So at test time also it is able to distinguish car and non-car. But if this model might not work better in real world cases. Now, because the data distribution is somewhat changing. Now, one similar problem we have in for hidden layer as well. So, this earlier problems we saw, this is for input layer. Now, similar problem we can have for hidden layers as well. So, distribution of a deep neural network's inner layer input changes during training as parameters of previous layers update, right? Slowing convergence. So, every hidden layer's output, like input, is also changing. Input also distribution is changing. So, that's what we are calling as input covariate shift. So, because layer 1 updates, then layer 2's input changes, layer 2 must adapt again. So, this is kind of a chain reaction we are having in the network. So, the core idea of batch normalization is we'll normalize or standardize activations at every layer or maybe few layers and keep distribution stable throughout the network. So, for hidden layers also, whatever the output will have, we'll just make the output normalized or standardized. Mean will be 0, standard deviation will be 1. So, in this case, I am just showing one example to make the idea very clear. So, without batch normalization, so let's say initially this layer's input distribution was like this and this layer's input distribution was like this. So, after back propagations, each backpropagation, inner layers input distributions will change. So, this layer's output will change. So, this layer's input distributions also will be changing. But if we have batch normalization, with batch normalization, you see, we are applying this batch normalization here. So, then in that case, for this layer's output will be having normalized. So, this layer's input also will be normalized. So, we'll have same normalized input distribution for the layers, hidden layers. Now, how batch normalization works? So, we'll use the same formula that we used earlier. We subtract the mean and then divide by standard deviations. So, we added one epsilon. This is the stability factor. And why we use this? To avoid the divide by 0 error, right? So, this is, I think, very easy to understand. Now, batch normalization works with mini batch because this mu and sigma, this mean and standard deviation, will be calculated from the mini batch. Now, for each feature, batch normalization calculates the mean and variance across the mini batch and uses these values to normalize the activations to have 0 mean and unit variance or standard deviation. So, this normalization, this is dynamic, so changes every batch. So, this is not like a fixed pre-processing step. After, for each mini batch, we have to do that. So, now when to apply this batch normalizations? So, this is one detailed image of neural network. So, then this Z layers, we are computing some linear output and then we are passing it through the activation layers to get this activation output, right? So, Z is basically Wx plus B, some linear output, and A is ZZ. So, Z is the activation function here. So, now where to apply this batch normalization? Before this activation or after this activation, right? So, that is something to think about. So, ideally we can do both. So, normalization before activation, this is the pre-activation approach. So, let's say this is the Z and this is the A. So, in this approach, you normalize the linear output before passing it through the activation function. So, from Z will calculate ZBN, batch normalized output, and then we'll pass it through from Z we'll get ZBN, then we'll pass it through the activation, we'll get A. So, ZBN is basically we'll apply this normalized standardization formula. This mu, this is calculated from the mini batch, sigma calculated from the mini batch, sigma epsilon is stability factor, G is the activation function. So, after this batch normalization, we'll applying this activation function. Next approach is normalization after activation. So, in this approach, the activation function is applied first and the resulting activation is then normalized. So, Z from Z we'll get A, the activation output, and then we'll normalize that. A, B, and this is the batch normalization output. So A will be Z of Z, that will be the activation output, and then we'll apply this standardization. Now both we can do, normalization before activation, normalization after activation, both we can do. Both are mathematically possible, but the original batch normalization paper suggests that normalizing the pre-activation approach, the first approach here, is more effective because it ensures the distribution is stable before it enters the nonlinear activation function. Now why it happens? So in this Z thing, right? So in this Z, we are calculating some linear output, right? So this can be in any range, right? So this is like, it can be very high values, low values as well. But in this activation for layer, we use either sigmoid, ReLU, tanh, different types of activation functions we are using. Those also squeezing the data between 0 to 1, between 0 to 1, minus 1 to 1, or 0 to the same exact value. So somewhat squeezing is happening in the activation layer as well. But so that's why before going through the activation layer, whatever the raw data we have, if we apply batch normalization on that and then we pass it through the activation, then it will perform better. So that was suggested in the batch normalization, original batch normalization paper. Okay, now quickly we'll see the how the neuron label calculation is happening, just to have the understanding. So let's say one neuron we have ZIZ, right? So Z11 we have, right? So let's call ZIZ. So the mini batch mean, it will be calculated from all the M samples. So let's say this is one mini batch and this is another mini batch, right? So for every mini batch, let's say we have M samples. So for this neuron also, any neuron we have, so this also for the M samples will have M output. We'll get average from the M samples. So that's how for a neuron label we'll get the. Similarly for standard deviation also, we calculate the standard deviation across M samples. So for per neuron, the thing will look like this. This might look a little bit complicated, but it's the same. The idea is that for every neuron, for M samples, we'll have M outputs, right? We'll take the average of that. Now, still we have one minor problem. So what we did in batch normalization so far is, whatever the input, whatever the layers output we are having, we are standardizing this. That means we are forcing this, mean is 0, variance is 1. What if for some data, we want different distribution? We don't want randomly changing distribution, because then in that case, every time the hidden layers will have to adapt to the new distribution. But let's say we want stable distribution, but that's not mean 0 and variance 1. Some stable distribution we want for an input layer, or say with some stable distribution we want for a hidden layer, but that's not necessarily mean 0 and variance 1. What if for a data, the optimal representation is mean 5, variance 20. So neural network need freedom to represent different distributions. So if we just use this mean 0, variance 1 or standard deviation 1, this thing, so it would destroy this freedom of neural network to learn better, the data, right? So what if we have different mean and different variance? How do we add that? What if we add some flexibility, like you don't need to be, like we can have different distribution and mean and variance doesn't need to be always 0 and 1. Then in that case we have to introduce some parameter, right? So model will learn itself like what should be the mean and what should be the variance or standard deviation. So that's the same thing we are doing. We just introduced one gamma and beta, 2 parameters. Don't look at this, this might look complicated. So normalization per neuron will be something like this, like, so we are subtracting the mean, dividing by the standard deviation, right? We are just will be adding some calculation that is just the opposite of this. We are just multiplying and adding. So multiplying by gamma thing and adding by this beta. So multiplying by gamma, so this gamma will be the scaling parameter and beta we are adding, that is the shifting parameter. So that's how this gamma and beta model will learn itself. So it's just one linear combinations we are taking, whatever the batch normalized output we got here, we are just doing gamma times that plus beta. So we are getting a new output. So that will be our flexible batch normalized output. So this is just the compact form we am representing here. So now we have the flexibility also. The model can learn different distribution, but that will is a stable distribution for a layer. Now the last thing is how it works in train time and test time. So train time we are sure we have mini batch. So for every mini batches we are computing this mean and variance, and that's how we are calculating, which is good. For any mini batch we are computing mean and variance, fine. But during test time we just have one sample to test. We don't know the mean and variance that time. How we will calculate that? How it has to go through this batch normalization layer as well, right? What will be the mean and variance in the for that test data? So for that, what we do is we maintain one running average during training. So during training only we compute this, we have this exponential moving average. So it's basically a very simple concept. So let's say mu run we are taking. So it will be, if we just take a running sum, it will be something like this: sigma beta, mu beta, or sigma run will be sigma run plus sigma beta, something, or you can take the squares as well. So this is the running sum, but we take one running average, and that's why we use one convex combination. So it's the same, mu run is 1 minus alpha times mu run plus alpha times mu b, and sigma square run is 1 minus alpha times sigma square run plus alpha sigma square b. So this is actually convex combination. So this is also does the same thing, but it keeps the value bounded between these two values, mu run and sigma b. So that's why this is preferable. It actually approximates two data distribution over time. So every time, for every mini batch we will be updating this, right? For every mini batch will this mu run will be changing by this mu b, right? So it approximates two data distribution over time, and it reduces noise from individual batches. So this running averages, running mean, running mu and sigma values will be using for test time. So during inference or test time, we'll replace batch statistics with running estimates. So we'll just divide, so subtract this mu run, divide by this sigma square run, right? So that's how at test time we'll be calculating the batch normalization thing. Now lastly, what are the benefits of course we have already discussed. I'll just summarize quickly. So without batch normalization, with batch normalization. Without batch normalization, you see the contours looks elongated and skewed, and it is ill conditioned. Sharp curvature in one direction, flat in another. So gradient descent follows a zigzag path, slow and unstable convergence, and highly sensitive to weight initialization. With batch normalization, contours are circular and well conditioned, similar curvature in all directions, and gradient descent doesn't follow. Gradient descent follows a direct path, smoother path, faster and more stable convergence, less sensitive to weight initialization. So here you will see, if you start from here, it will take more time. From here, it will take less time. But here with batch normalization, doesn't matter from where you are starting, it will take almost same time. So we saw this benefits: faster training, more stable optimization, less sensitive to weight initialization, improves gradient flow, enables higher learning rate. So in this case, you see though we have zigzag path. So if you take larger learning rates, of course there are chances of overshooting here in this case, right? So but in this case we have stable path, so we can use larger learning rates. So learning will be faster. Now, lastly, it acts as a regularization. So, what regularization does? So, it prevents the overfitting, right? So, batch-wise statistics, this mean mu and sigma we are using, right? And also we introduce some flexibility parameter like gamma and beta. So, all this introduce some noise during training. So, right? So, and hence some regularization effect we have. So it's not as good as other regularization techniques like dropout, but we can use batch normalization along with dropout to add some regularization